Hello, and welcome back to Tomography. So this is like lecture 6 or so out of Tomography, I think. So thus far we've covered the radon transform and back projection and all that, and right now we're in the middle of trying to build up to the Fourier transform. But before we talk about the Fourier transform, I want to talk about this a collection of functions that we can do the Fourier transform on. Ultimately, by starting with this collection of functions, which is called the Schwarz space, we're going to be able to define members of the dual of the Schwarz space, which is called the tempered distribution. Tempered distributions include things like periodic functions, which you can't normally take the proper Laplace transform of, and also include things like the delta function. And all of these aren't actually functions, or well, the periodic functions are, but the delta function isn't. But these aren't integrable functions, either not integrable or straight up not functions. But it turns out that they all live inside this collection of tempered distributions over the Schwarz space. And using distribution theory, we can actually ultimately define a Laplace transform on them. And so this will allow us to do a lot of things like, like coming up with Fourier series for periodic functions, Shannon sampling theory, Nyquist frequencies, and things like that. And ultimately, this will all feed into signal processing. So thus far, we've gone over a definition of the tempered distributions and what they are, which are continuous linear functionals. We've had a few examples. So we had delta functions. So evaluation of a function at a point, say 0, is the Dirac delta function, and so yeah, that is a linear continuous functional on the Schwarz space. Now, you can also take derivatives in the Schwarz space and then evaluate there, and those will give you more functionals. And so we have a whole collection of them right there. But there's a whole lot of other ones, and here and there we'll use others. But we can build up our database of tempered distributions by looking at transformations on them. And so this lecture is all about operations that you can do on tempered distributions. Now, before, when I ended the last lecture, we talked about multiplication of a function by a tempered distribution and how that can give you another distribution. But today what we're going to talk about are things like derivatives of distributions, shifting distributions, reflecting distributions, and etc. And ultimately this will build up into the idea of the convolution theorem and convolution of distributions with regular functions. And so the convolution theorem out of Fourier transforms will basically say that the Fourier transform of a convolution of two functions, or a distribution and a function, turns into the product of the Fourier transforms. And this is much like what you saw back when you were in undergrad looking at differential equations. So anyway, so that's what we're going to be doing today. And it turns out that what we're going to do each time is we're going to take a look at regular distributions. Remember, that is a distribution that can be represented by a function. And we're going to justify all these formulas for a distribution by looking and seeing what happens to a regular distribution. So, for instance, when we take the derivative of a distribution, we need to define what that means. Well, if we take a function and replace it with its derivative and look at that regular distribution, then we can go ahead and move the derivative off of that function through integration by parts, and it moves on to what we're inputting. And then that allows us to describe, say, what a derivative of a distribution is, and etc. So that's the idea, and that's what we're going to be doing today. All right, so that's enough blabbing from me, and why don't we go ahead and get into it. Okay. So, welcome back. So today we're talking about operations on tempered distributions. And so let's go ahead and talk about that. So operations on tempered distributions. And I tried to start this last time, and I realized sort of halfway through that like it really we should do more dedicated work. So yeah, just dedicate a whole lecture to this, because this is how we're going to define derivatives of distributions. We're going to define multiplication of functions by distribution, which we did last time, and a few other properties. So so last time what we said is that if, say, f is a function of polynomial growth, which basically means that f of x is less than or equal to c times 1 plus the absolute value of x to d over 2 and x squared here for all x in Rn and some d in n, and if so basically means that, and if d beta f is also of polynomial growth for all beta multi-indices, then what we have, it turns out that f times t is a tempered distribution whenever t is a tempered distribution, and by that we mean that the tempered distribution tf acting on some phi in our short space S, it really can be expressed this way. So for all phi in S. And so we showed a critical idea last time was really to show that this guy is in short space. And that follows from f being infinitely differentiable and polynomial growth. So, okay. So, yeah, and we concluded by saying that f times delta is the same as f of 0 times delta. And that's, yeah, that isn't always going to be true, but for the delta distribution, that ends up happening. So now we're going to talk about derivatives of tempered distributions. And this would work for regular distributions too, but we're talking about the tempered distributions for the sake of the short space. So basically what we can do is first we're going to consider, consider the regular distribution. Corresponding to some f inside short space. Then what you can do is you can see that if you take tf times phi, rather the derivative with respect to alpha for some multi-index of f and hit it against phi, that's going to be another regular distribution because we know that derivatives send short space functions to short space functions, and so this will give us another regular distribution. And if we want to evaluate what this is, that is the same as, say, t df comma phi, and this is the integral over Rn of d alpha times phi, f, sorry, d alpha f of x times phi of x dx. Okay, so what can we do from here? Well, we can use integration by parts, and that's going to give us -1 to the absolute value of alpha Rn of f times d alpha of phi of x, and it should be f of x there, dx. Now, integration by parts usually includes some boundary terms, but since f and phi are both rapidly decreasing and going to 0, all those boundary terms just vanish, and so all we're left with is that last term for the integral, and that basically transports the derivative off of f and puts it on phi, right? And what is this? This is -1 to the absolute value of alpha of tf against phi, right? And so that gives us a sort of motivation to declare what the derivative is of a distribution. And so we'll go ahead and maybe do this in green. So definition. So we're going to suppose that T is a tempered distribution and alpha a multi-index. The alpha distributional derivative of T is the tempered distribution d alpha t, so this is a notation, defined as where we take d alpha of t, hit it against phi, and this gives us -1 to the absolute value of alpha of t against d alpha phi. So really what we're doing is we're defining the derivative of the tempered distribution t, so we know what t is, and so we say the derivative is whatever happens when you do this combination of taking the derivative of phi first and then hitting it against t, and that'll give you some other distribution, and we declare that distribution as d alpha t, right? So this allows us to do things like define derivatives of the delta function, and second we're going to talk about the Heaviside step function, and all of these are functions that don't traditionally have derivatives, but they admit a tempered distributional derivative. Okay, and so we have another definition here. If TF is a regular distribution, whose distributional derivative say is also a regular distribution, say t. Then what we say is we're going to write basically Rn of g of phi dx is equal to -1 to the absolute value of alpha, magnitude of alpha, integral of Rn of f against d alpha phi dx for all phi and s. And we say that g is the weak derivative of f. So f might not actually be and I guess it should also say and g is equal to -1 to the absolute value, or sorry, and g is equal to d alpha of f. Okay, so so what we're going to say here, basically we could have functions that say f that aren't actually technically differentiable, so they might have jump discontinuities, but they might define a regular distribution when you take the derivative, so those sort of discontinuities might vanish. And if those do, then we say that f has a weak derivative I actually think jump discontinuities might be ruled out, because those should actually get you delta functions, which are singular distributions, and so singular distributions we know aren't regular. But if you say have holes in your function or something like that, then you're still pretty good. Okay, so now let's take a look at one example. And so let's switch back to blue. So we're taking a look at example here, and we're saying that we're going to let f go from r to r. So this is just a single variable function. And so we have f of x is equal to 0 and x, and so it is 0 if x is less than 0, and if x is greater than or equal to 0, it is x. So we are looking at the function that is this. So here, and then like that. So we know that if we take the derivative here, then we're well defined everywhere but this, and so we should get something like this, but we don't say that f is differentiable, or at least not differentiable over Rn, because that's a whole. And so maybe I should stay consistent here. Let's put a red. There we go. But it turns out it is weakly differentiable, and it gives you exactly what you think you would get. So so what we do is we go ahead and we take a look at the regular distribution, and we're going to try to, and we want to take the derivative of it. So we're going to say that, we're going to say well, here we'll just say d by dx of t sub f against phi is actually going to be equal to the is going to be equal to minus of f against phi prime. And if we go ahead and write this out, is minus the integral from 0 to infinity of x times phi prime of x dx. And if we do integration by parts again, we're going to have the integral of phi of x dx 0 to infinity, which is the same as if we multiplied phi of x by h of x times phi of x dx, where this is h of x. So this is at 1 and this is at 0. And so it would kill all the phi values on that for the negative values, but it wouldn't change them for the right hand values. And so this is the same as, say, h against phi, if you'd like, and where h stands for the regular distribution. Okay, so we have that f is weakly differentiable with derivative weak derivative h. Generally speaking, in functional analysis, whenever you say something happens weakly, usually you mean that it happens underneath the integral sign, or it happens within some sort of inner product or dual product or something like this. And so here we have sort of both of those. We have this dual product, and we say that we are differentiable when we can sort of express this derivative. We have the identification between the derivative of a function that we think it should be, and etc. But all under the guise of a dual product. So we can try to take this further, and this is a little bit trickier. So we start off with the Heaviside function here. So this is at 1 and 0. So this is h of x. So you could ask, what is, h prime of x, where we're using sort of an abusive notation here. And so, so we can go ahead and try to do that. So basically, what we're going to have is we're taking a look at h prime against phi, and that should be minus h against phi prime. And so then if we take a look at the integral negative of the integral 0 to infinity of phi prime of x dx. That is in fact what it gives us. Well, we can rewrite this as the limit as n goes to infinity of the integral from 0 to n of phi prime of x dx, and then we can use a little bit of fundamental theorem of calculus, and we get at the limit as n goes to infinity of phi of x evaluated at 0 and n, and so then this is minus the limit as n goes to infinity of say phi of n minus phi of 0, and well, phi of n as n goes to infinity is going to go to 0, and so ultimately this gives us phi of 0. But we know that phi of 0 is equal to delta against 0, and so therefore we can say that h prime of x is weakly differentiable, and its weak derivative is the delta function. Well, we can't say it's weakly differentiable, but we can say this tempered distribution is the distributional derivative of h is the delta function. So but as delta is not regular, h is not weakly differentiable. Okay, so what we know is that you're weakly differentiable if your derivative is a regular distribution, and since the delta function is a singular distribution, that means that h can't be weakly differentiable. Okay. So now we can take it even one step further. Ask, what is delta prime? Well, delta prime against phi should be equal to minus delta against phi prime, which would be equal to minus phi prime at 0. And this itself is another tempered distribution. And so we just call this the derivative there. And so, and more generally speaking, we say that the kth derivative of the delta function is the tempered distribution that gives you, say, -1 to the k of phi to the k 0. So the kth derivative of phi evaluated at 0 times -1 to the k, and that is the kth tempered distribution of the delta function. Okay. Okay. So what is the next transformation we want to take a look at? So we've talked about derivatives, and we've talked about multiplying by functions. And so now we're gonna, when we did the definition of the of the distributional derivative, we motivated it by taking a look at a function, and so or a regular distribution first. And so again, we're going to talk about a regular distribution first here. And so so we're going to say for each h and say Rn, we define the translation operator. So we're going to have tau of h, which will send from s to s and so it's basically what you think it would be. So tau sub h of f evaluated at x is going to be f of x minus h. Right, so this is how we would define it on a function. So how we're going to define it on a tempered distribution, it can follow first by taking a look at what happens when we apply the regular distribution. Tau corresponds to tau sub h of f against phi. I'm sorry, I should probably put a comma there. And what is that going to end up giving us? Well, that's going to be the integral from over Rn of tau. I'll see if I can get this done in time. Of tau sub h of f of x times phi of x dx. Right, and so we know this is the integral from over Rn of f of x minus h to phi of x dx, and this is, after a substitution, will get you to f of x and phi of x plus h dx, and so this is the same as the integral over Rn of f of x times tau of minus h of phi of x dx, and so that gives us our hint of what we're going to be doing. So this is the same as saying tf against tau of minus h phi, right? So this whole thing gives us the translation operator being applied to temperate distributions. So basically tau sub h acting on temperate distribution t is given as the temperate distribution that does this. So basically tau sub h t acting on phi is equal to t comma tau minus h of phi. Okay, so now we can do similar things. For instance, we can, if we let r going from s to s be the reflection operator, and so this again happening to a regular function would be r of f of x equals f of minus x. Then we say that r sub t, which is going to be in a temperate distribution for t and s, is given as r sub t acting on phi, which is equal to t of r of phi. Okay, for all phi and s. And so again, we're defining all of these operations on our distributions by doing something to our short space function first, right? So we say, all right, so if we're going to think of it happening to t over here, well, instead of, coming up with some weird way of defining it for t, we're just going to hit it on phi first, and then we declare that this overall distribution, which is still a distribution, is our new temperate distribution. Okay, so now we need to talk about the big one, and this is convolution. And so, all right, so the convolution of two test functions, say phi and psi in S, is defined as phi star psi of t, of x, and this is equal to the integral over all of Rn of phi of x minus y times psi of y dy. Okay, now whenever you're talking about convolutions, generally speaking, the arguments of each of the two functions involved should always add up to the same thing no matter where you are, and so in this case they add up to x, right? And so that's the convolution defined here. And so we would like to be able to talk about the convolution of temperate distributions and other things like that. And so, we're going to build up to that. But first, we have a little proposition, and might be good homework just so you get your hands dirty. But so for any phi, psi, and omega in S, we have And again, this is coming from applied analysis, the textbook that I told you about before. And so for A, we have phi star psi equals psi star phi. So it commutes. The order does not matter. We have the associativity property. So phi star psi star of omega is equal to phi hitting on psi hitting on omega, right? So it doesn't matter which two you perform first. And C, and this is interesting, the translation operator acting on phi psi convolve psi is the same as the translation operator hitting on phi against and then convolving with psi, and we can also move the translation over on psi itself, for all h in sorry, not s, rn. Okay. So now we can go back and we can re-express the convolution as a combination of operations. So we can say that phi convolved with psi at x, we can rewrite this as the integral over Rn of the reflection operator hitting on translation operator corresponding to x, not h, on phi. Evaluate this at y, and then take psi of y dy, and we can see then that this is actually just r tau x of phi against psi, so where we take this as sort of the regular distribution. Okay, so then we can talk about convolution. Thus the convolution of phi with a tempered distribution T, say in S star, may be defined as, and so we're going to say that phi being convolved with a distribution T evaluated at x is equal to T against R tau x phi. Okay, so we saw that it would work out for regular distributions here, and so now we just extend that same idea over here. So what this allows us to do then is it allows us to convolving test functions with distributions with delta functions, right? And so then we get phi convolved with delta at x is equal to delta against r tau x phi, like we just said, and that is the same as r of tau x phi evaluated at 0. But what does all this mean? At 0, sorry. If we start unpacking that, we have r of phi, we do the translation, so it's going to be 0 minus x, and then the reflection, it gives us phi of x. So this allows us to write sort of an abuse of notation, the integral over Rn of delta of x minus y against phi of y dy is equal to phi of x. And so this will be used a lot in the future. Okay, so that sounds like a good place to stop. All right, so so this was really quick. I just want to go over a whole bunch of quick little transformations of distributions and temporal distributions, and just really wrap out the basics of a lot of these distributional theories. The last thing that we really need to talk about is convergence of distributions, which I'll go over next time, and that allows us to do things like come up with like approximate identities and whatnot, which is something like what we did last time, like 2 or 3 lectures ago, when we were proving Reynolds inversion formula. And so this gives us a different approach to the same sort of idea, and so we will get through it, this sort of limit of intervals function evaluation, or get basically approximations of the delta function, and those are really, really important for signal processing. Okay, so I think I'm going to end with that, and yeah, all right, take care. Okay, so that was distributions, or operations on distributions, and so hopefully that was somewhat coherent. I was really tired when I put that together. It was like right after lunch, and I was trying to cram it into an hour of free time that I had, quiet time. And so it might sound a little groggy and stumbly, and I apologize for that, but I mean, that's just the way it is with trying to record on a deadline. Again, we used the book Applied Analysis by, I can't remember the author's names, Hunter and somebody else. I'll put it here, over at UC Davis. And so I appreciate them putting that book together, because that certainly has made my life a lot easier. This was straight out of chapter 11 and is one of their sections. I skipped a few examples that aren't really going to be relevant to us later, but good to know. All right, so I think I'm going to stop here, and yeah, have a good day.